answer is yes, right? And that is specifically very clear for SU3 in the standard model. The conserved charge is color, right? You have these three colors, R, G, and B. You have also the anti-colors, anti-red, anti-blue, and anti-green, right? So it's a total of three colors, three anti-colors. And this is conserved by SU3. SU2 gets more complicated because it's spontaneously broken, right? So the charge is not manifest in the low energy theory, the charge conservation. Although it is conserved, it manifests in more complicated ways. I hope I'll be able to show a little bit of that. But when the symmetry is exact, there's always, as long as it's a continuous symmetry, a continuous transformation, there is a conserved charge. Okay. So, any other questions which were, okay. In the case of SU2, you will have something similar to a SU2 color, right? Which is a number that goes from 1 to 2. We would have to name it something, right? And so you have these SU2 doublets, right? The main thing I have shown you that is SU2 symmetry is the proton-neutron pair, right? So these would be color number 1, color number 2, and that would be conserved, right? And it's the same with the quarks, right? You have those three colors. And you also have the anti-color, let's call it like that, right? For U1, you have just one charge, which is the electric charge, but you also have the anti-charge, right? Things can be positive or negative. In practice, if you count it like that, you have two charges. Right? So it's the same here. These I could name these, I don't know, plus, minus, something like that. Right, or 1 and 2, and there would be 1 bar, 2 bar, and that would be conserved. It's the same story. Right? In the standard model, because of the symmetry breaking, you can have emission of W's that transform one guy into the other, right? And then it's trickier. It's still conserved, but it's trickier to see. Right? Okay, so now I just a quick recap of the last thing we did, right? I told you, when you impose these abelian local symmetries around, gauge symmetries, right? You have to introduce a gauge boson in order to keep your Lagrangian invariant, right? And that's the simplest case. If you go to the non-abelian case, where these guys now transform as complicated objects, you have to see, right? This is a matrix that can, the size of this matrix will depend on which representation the fermion is and the size of these generators, right? So the simplest example is when you have this representation I was writing here, which is the fundamental of SU2, and then these generators are just Pauli matrices, right? And this exponential is understood as the sum, right? The Taylor series of Pauli matrices. So this U here is a matrix, a 2 by 2 matrix, right? That means that this is a two-component object, right? Where this matrix acts, right? It can be more complicated for color, for instance. These are Gell-Mann matrices, which are 3 by 3, and so this is a three-component object, red, blue, and green, right? Now, the gauge boson transforms in a more complicated way because it always comes together with these generators, right? What really transforms under the gauge transformation is this contraction of a number of gauge bosons, one for each generator, with the matrices. And this, of course, transforms as a matrix, right? You apply the same transformation from the left and from the right, and you transform the matrix as an operator. If you do the infinitesimal version of this, so I take this exponential from the right and the left and expand and take only linear terms in alpha, this becomes more comparable to what we have up there, right? You see that each of these gauge bosons, remember, this index goes from, in the case of SU2, from 1 to 3. SU3 goes from 1 to 8, right? That's the adjoint representation of the group, right? But each of these gauge bosons transform in a way that is very similar to the abelian case, plus a very important piece, which is the non-trivial part for non-abelian gauge theories, right? This will generate all kinds of complications, and you see this is the structure constant for the group, which is essentially given by the commutators between the generators. So you see, if you go to the abelian case, this must be 0 because they commute, right? All the generators commute. This must be 0. You go back to that transformation up there, right? So the infinitesimal versions are easier to compare. That will have another consequence, right? Again, I'm just repeating the abelian case. You have to exchange the derivatives on the fermion by a covariant derivative, and that will generate an interaction, right? If I just plug this in here, I have a term which is just the usual kinetic term, but you have a new piece which generates a fermion-fermion gauge boson interaction. That does not change too much, right? The covariant derivative is now this one, right? When I plug this in here, I get an interaction that is fermion gauge boson, right? And a usual kinetic term. The only difference now is that you have this matrix here, which will end up in the vertex. And that means that when these guys, they are many component objects, right? It's easy to understand with the quark, which is red, green, and blue, right? In the vertex, you have a Gell-Mann matrix, right? The generator. That means if the guy was pure red before emitting a gluon, it will rotate. It will end up in another combination of colors because that matrix is involved in the interaction, and these guys are not diagonal, right? So they mix. When a quark emits a gluon, it changes color. When an up quark emits a W, it becomes a down quark, right, for instance. So you have these effects which are intrinsic to non-abelian gauge theories, right? And finally, you have F min, right? F min times F min was the gauge invariant kinetic term that I could build for the gauge boson, right? That is still true now. I can still build something that is gauge invariant. It's now F min A square, right? But now, because of this new piece, right? F min now must carry this new piece. And you see, when I take the square of this, I'll have terms that involve 3 gauge bosons, right? Which is a cross term between this guy and one of those. And I will have a term which is this last term square. So now I have interactions between gauge bosons and themselves, right? There's self-interaction for gluons. And these are the 2 vertices that you get for any non-abelian gauge theory, in fact, right? I'm using gluons because that's the example we have at hand, right? But the same is true for the W's and the Z's. They interact between themselves. Huh? So that's it for non-abelian theories, right? And now we want to go forward, right? We want, worthy of note, right, is that we can still, that didn't change. This term, mass term for gauge bosons is still forbidden. This is just not gauge invariant. It was not in the abelian case, and it is not in the non-abelian case, so we still have no mass, no way so far to give a mass to these gauge bosons. Of course, the answer is over there on the left, right? But we'll get to that soon. Right? So now, how do we find those symmetries? Right? I'm talking a lot about building symmetries into my Lagrangian, right? But what symmetries should I put in, right? How an experimentalist starts noticing symmetries. And the point is that Noether's theorem, right, one of the most important theoretical achievements of early 20th century, right, is this and Einstein stuff, right? This changed the whole game of theory in physics. That using Noether's theorem and what Einstein did with it is we started predicting stuff before seeing it experimentally, right? And this is one of the main things, right? We realized, right, Madame Noether realized that if you have continuous symmetry, that implies conservation. Classically, that's easy to show, right? If the action is invariant, you just use the extremization of the action and the equations of motion, and you show that will always be a conserved current. And the component 0 of this conserved current is a charge density of some sort, right? And you have also the possibility, right, for the action to be invariant, you can get an invariant action even if the Lagrangian is varying. as long as the variation of the Lagrangian is just a total derivative. Remember, the Lagrangian is inside an integral for the action. We will be interested in the case where this piece is 0. So the Lagrangian is really invariant, right? So then this current is a little bit simpler. This part, which is this surface term, this total derivative term, does not matter for us, right? And then you get these currents, right? So a few examples you can see here. There's a lot of symmetries you know, right? And this is the conserved quantity that arises, right? So time translation leads to energy conservation. Position translation leads to momentum conservation. Invariance under rotations, 3D rotations, leads to angular momentum conservation. And these internal symmetries, right? These phases, now that have nothing to do with space-time, they lead to charges, right? So U1 is usually just a number conserved, right? And for the non-abelian ones, it will be depending, is the answer to his question, right? It will depend on the size of the group, how many charges you have, right? Each group has its own structure, right? It depends essentially on which size are the representations that the group support, right? The irreducible representations, right? So that's how we see, because these conservations, they will end up in Feynman diagrams as selection rules, right? So you can see straight out that if I demand a U1, these guys can only show up in the Lagrangian in pairs, right? Because I have to have exponential and minus the exponential of minus the phase, right? So these guys only show up in pairs. That means that any vertex in my theory will always have two interactions of that field. That alone guarantees charge conservation, vertex by vertex in my theory. That forbids, for instance, that an electron will decay just in photons, in a number of photons, right? There's no way. There's another operator that is acting there that is either annihilating an anti-electron, and then you can have electron, anti-electron going to photons, or creating an electron to the future, right? Which is this case where the electron just emits a bunch of photons, but continues on, right? And that happens for every one of these conserved charges. So essentially, the way people started seeing these symmetries in experiment was noticing that some particles would never decay in certain ways, right? And then you discover a lot of charges. The most famous one is probably strangeness. That's why we found the strange quark, right? Which was a number that every time you produced kaons, right, these mesons with strangeness, right? That's why they were called strange, is because they were very easy to produce, but they were always produced in pairs, kaon, anti-kaon, right? So there was some strong interaction that was able to produce them. That's why the probability of producing them was high. But then they would live forever in the scales people were used to, right? They would live very long times because the only way they could decay is in non-strange particles because they were heavier. Strangeness also came with some extra mass, right? So what people figure out from this is that there was the interaction that was producing these kaons conserved strangeness, which was a charge. So it had to be producing kaons and anti-kaons, so strangeness plus 1 and minus 1, total 0, right? But then these guys moved apart, and for a guy that had strangeness 1 to decay, it had to decay through another interaction that violated that conservation, disappeared with strangeness. And that second interaction was a much weaker force. Those are the strong nuclear and weak nuclear forces. That's how they found out about those. And that you had a charge called strangeness that was conserved by one of the theories and not by the other. So there was a piece of the Lagrangian and only involved QCD that conserved strangeness, but the weak force didn't, right? So that's the way you find these symmetries, is based on these conservations, right? You start, of course, you have to do a huge puzzle solving, right? You have all these decays and you have to figure out what is being forbidden or not. It's not a trivial problem to see the symmetries there, but in the end we managed, right? So now, what we want to do is build the standard model, finally. I intended to get this by the early last lecture, but here we are, right? And this is today's periodic table, right? That's what we know about the makings of the universe, right? You notice there's no graviton there because we are not sure there is a graviton, right? There's a consistent theory for a graviton. I mean, fundamental one, right? But what we want to understand now is this division, right? Why do I call some guys quarks? Why I call those other guys leptons? Where those come from? What's up with this guy, right? And the whole point here is that the whole table is built on these three gauge symmetries. So there's only three couplings, right? You might notice that every time I introduce a local symmetry, I introduce a coupling, right? This is one coupling, because there's only one symmetry. Here I have three constants, right? Which we call G strong, G and G prime, right? GS, G and G prime. This are the three gauge couplings, right? And then I have to decide how many fermions and scalars are transforming under the symmetries. The gauge bosons themselves are fixed by the symmetries, right? But not the fermions. I could have, in principle, 40 fermions, right? That would be a problem for QCD, but you could, in principle, live in a universe like that, right? So now let's understand how we build this guy, right? And the main point here is that chirality matters, right? This is the most ugly thing you face when you're trying to learn the standard model. Is the one that bothers everyone. It bothers Pauli, so you can feel good being bothered by it too, right? So apparently Pauli at some point said, even joking with Einstein, right? He said, oh, maybe God does play dice with the universe, but I'm sure he's not left-handed. and it was a joke with this, right? This is in Leon Lederman's book, so if that is a lie, it's his fault. But in any case, that's attributed to Pauli. And the thing is, chirality, as I said before, is this property that we see in a lot in biology systems, right? Sometimes a molecule can have a right-handed configuration and a left-handed configuration, right? And that's easy to understand for my hands, for instance, right? I have a right hand and I have a left hand, and they are different by a transformation of parity, right? In fundamental particles, it's kind of odd, but it's not much more odd than having angular momentum, for instance, right? We know that electrons are not rotating little spheres, right? That's not what spin is, right? If you try to figure out how fast that little sphere should be rotating, you get higher than the speed of light for the sphere, right, on the edge of the sphere. So that's not what spin is, right? It's an intrinsic angular momentum. And particles can have intrinsic chirality, even if they have no size or no internal structure. So that's what I'm talking about. In terms of operators, the chirality is defined in terms of this fifth Dirac matrix, right? So in 5 dimensions, it's possible to construct a 4x4 matrix that anti-commutes with all the other 4, right? Gamma 0, gamma 1, gamma 2, and gamma 3, right? And this guy has all these properties that I'm listing here, right? It's also Hermitian in the representation I'll be using, right? And you can build these 2 operators here. Right? And these 2 operators have the important property that they are projectors. So all of these, right, tells you that these are projectors, right? If you apply the projector in a fermion to project it into the right hand, and then try to project on the left, that's 0. Projecting twice is the same as projecting once. Right? So all these properties you can show straight from this definition. That's an exercise. Right? But the important point is here. Right? Because of this property, right, I can just substitute an identity here and write it like that. And that's the fermion projected in this left-handed fermion. And this is the fermion projected in a right-handed fermion. Right? So I can always write any Dirac fermion as a sum of left-hand and right-hand components. Right? In terms of interpretation, it's easy to understand chirality when the particle is massless, without a mass. Because in this case, you can diagonalize, right, the operator, that operator that gives you chirality. At the same time, you diagonalize helicity. So helicity states and chirality states are the same. And what is helicity? Helicity is the projection of the spin in the direction of the momentum of the particle, right? So you can have the spin pointing forward in the direction the particle is moving, or backward, right? The projection of the spin. And that's helicity. That's plus helicity when it's the same direction, and that's minus helicity. Helicity can be plus or minus when it's in the opposite direction. And that coincides with right-handedness and left-handedness. The two operators coincide for massless particles. And that's a good quantum number for massless particle because you cannot move faster than a massless particle. So if the spin is pointing in the same direction of the momentum, it will be pointing in the same direction of the momentum in every reference frame. But if it has a mass, I can run faster than it. The spin will be in the same direction, but now I see it moving the other way. So when the particle is massive, then helicity is not a good quantum number anymore. It varies from one reference frame to another, right? But chirality still is. So for massive particles, they do not coincide anymore. The eigenstates of chirality are not the eigenstates of helicity anymore. So chirality is really an intrinsic property of these fields, and then by consequence, here I'm always talking about the field, but I'm thinking these fields create particles, right? And the particles will have this quantum number, right? So, and more importantly for us, right? So you can understand chirality in this way, but try not to be confused, because it's very easy to forget that in the case of massive particles, chirality and helicity do not coincide anymore, right? But more important for us is that chirality eigenstates are not mass eigenstates, right? That's the trickier part for massive particles, right? Why? Because if you use the properties that I have shown before, and here's another exercise, right? These are just definitions, right? This is the definition of psi L bar. You first project and then you take the dagger and the gamma zero, right? And this is just a reminder that you can take a representation for this guy where it is Hermitian, right? And if you take this, it's easy to show. You just put PL and PR here and commute with gamma mu. It's easy to show that if you have a gamma mu in the middle of these two fermions, this will turn out to be a sum left, left, right, right, right? But if you have no gamma mu in the middle, right? And this is what happens for the kinetic term of fermions. This is what happens for the interaction with gauge bosons, right? So in all of those cases, I will be able to expand just on left, left, right, right. But in the case of the mass, because I have no gamma mu in the middle here, this becomes psi L, psi R, psi R, psi L. It's missing a mass here. Right? Should be a parenthesis here and there. Right? The mass is multiplying everything. So that means that if I look at this guy, this is the guy that has a well-defined mass. But these guys, as they propagate, I can draw diagrams like that, which are transforming left-handed and right-handed guys, right? So the way to interpret this is that a mass eigenstate is a mix of left and right-handed for massive particles, again, right? It's a mix of left. And you can choose to use one basis or the other, right? We would never be talking about this if the interactions of this guy were the same as those, right? But the fact is, as Pauli lamented, that is not true, right? So now, what happens in the standard model is that the SU2 left, that's why it's named like that, right? And the U1 hypercharge are sensitive to this, right? So the U1 hypercharge is just a U1. We call it hypercharge to differentiate from the electromagnetic U1, right? This is a different charge. We call it hypercharge. And things will transform like that under this U1, right? I removed a number in here. What this number does is, in a way, changing the representation under U1. That means that if suppose I take two different fields, one that has y equal to 1, one that has y equal to 2. If theta is 2 pi, one of them will have rotated once in this space, the other one will have rotated twice. So this kind of tells me how fast they rotate when I do the same transformation for both, right? And that will imply on the charge of the particles. We'll see later. So I have a freedom of choice. When I make things transforming under U1, I can choose a value for this y, right? And this is the choice of the standard model, right? What I want you to notice here is that quarks and leptons have different hypercharges. I'll justify these numbers later, right? In the end, it's all experiment that is behind this, right? I could choose any number, but in the end, it's really experiment behind everything. But more importantly, you see, the left-handed guys, I do not differentiate from the quarks on the up row here from the down row here. And I'll see the reason for that in a second when I talk about SU2, right? They have the same hypercharge, both the up left and the down left quarks. Same for the leptons, right? But on the right-handed part of the diagram, each of these rows have a different hypercharge. And this one in pink is not strictly part of the standard model. I'll make a point for that later, right? But we're not even sure there exists such a thing as a right-handed neutrino, simply because we have never seen it anywhere, right? So we're not even sure that guy is there.
You comment about the arguing states of mass. Does this have anything to do with neutrino mixing?
Yes. Yes, but I don't think we'll get that far, right? But the thing is, you have, at some point, to diagonalize your Lagrangian. I'll talk a little bit, even maybe give an exercise, a simple exercise about that. But if you have terms in your Lagrangian that do something like that, right, where you have some particle created by one field here and a different field there, that means these guys are not really particles as we understand them, right? They are becoming each other, right? But maybe the interaction here produces a phi, and the interaction here absorbs this other guy. But the propagation is not the one with an eigenstate of mass, and that's the particles you see propagating, right? So then you have to diagonalize your Lagrangian to have mass eigenstates, but those guys will not be the interaction eigenstates. That's exactly what happens with neutrinos, right? You produce electron, muon, tau neutrinos, but the guys that propagate and are eigenstates of mass are not the electron, muon, tau neutrinos. Are neutrinos that we call just 1, 2, 3, right? And those are coherent states of electron, muon, and tau neutrino. But in order for that to happen, the neutrino must have a mass.
And there's some connection with that with the right hand and left hand?
Yeah, maybe. Then the question is maybe. Maybe you can do that. The point is that this oscillation demands that you give mass to the neutrinos, and you can ask me how we get a mass for the neutrinos. One way is to put a right-handed neutrino. The other way is to assume that the neutrino is a Majorana particle. I think you talked a little bit about Majorana fermions already, right? And then you don't need the right-handed one, right? So there's more than one way of solving that problem. We don't know which is the solution that nature chooses, right? We need more data in order to know. But in any case, I'll talk a little bit about the mass of the fermions tomorrow, and then this discussion can be made more concrete, okay? So this is the layout on how those particles transform under the U1, right? But chirality also matters, and it matters even more for the SU2 left, because now I'll take these two projections of my fermion, and the left-handed one will transform under SU2. Remember, these are Pauli matrices. Right? And the right-handed guys won't even transform. They just don't have that interaction. That interaction only happens with the left-handed part of the fermion. Right? So every time a W hits a fermion, it's projecting out from this coherent state, which is left and right, is projecting on the left one. In fact, the physical W is more complicated than that, but the pure gauge boson for SU2 would project on the left-handed configuration, right? Because it measures, only interacts with this guy, right? And then under this, right, since these are Pauli matrices, these guys need to be two-component objects, right? This is again the isospin that we saw for the proton and the neutron. In fact, for the same reasons. In the proton and the neutron, to transform a neutron in a proton, all you have to do is replace a down quark by an up quark. Right? It's the same symmetry, but now we're seeing it happening in the quarks and not the whole proton and neutron. Right? So these guys all come in doublets. And that's why they had the same hypercharge. There's no, the particle that actually enters into the model is a left-handed electron doublet, which is a combination of electron and the neutrino of the electron, the left-handed part. Right? Under SU2, they are indistinguishable. Right? What will distinguish them is the electric interaction, right, after breaking. So all the left-handed guys come in pairs, and that's why they had, let me try to go back, they had to have the same hypercharge. There's no difference between the up left and the down left quarks. They are part of one particle they are called left-handed quark that has an up configuration and a down configuration. The crazy thing is that it only applies to the left-handed part of the model. The right-handed, no. You see, the up right and the down right. I'm always talking about the first family, calling up and down, but the same is true for charm and strange and top and bottom. It just repeats. Right? This guy is different than this one by hypercharge if you look at the right-handed part, but not on the left-handed part. Right? Together, right? So I can define these three new particles, right? A quark, all of them are left-handed, right? And I'll combine that with the right-handed part of these fermions, right? But altogether, these two symmetries forbid completely mass terms, right? I have shown you that you can write psi bar psi as psi bar left, psi right, plus psi bar right, psi left, right? In fact, you showed that in the exercise, but once you see that, right, this part and this part have in common that if this guy transforms differently than this one, this is not invariant, right? And he's explicitly what you get. So this TA here and YL here is coming from this guy. This is coming from this, right? The Y's are not equal, so in here I'm using the electron as an example, right? So YL for the electron is -1, Y right is -2, so it does not cancel. And this part is even worse, right? This is a two-component object. This guy is a one-component object. So even the product here is not giving me a scalar, and the action should be a scalar, right? You don't have a matrix, an action that is a matrix, right? So even the product makes no sense. Right? So mass is completely forbidden for all fermions, right? Which seems to be a problem. And it gets worse, right? Because now if you go to the gauge sector, right? If I'm saying, well, I have U1 times SU2 times SU3, right? We have seen what happens when I make these things local. I get gauge bosons, right? I get one gauge boson for U1, 3 for SU2, because that's the number of generators of SU2, and 8 for SU3, right? But they are all massless, right? I told you a few moments ago, this term is forbidden. Right? Now, you look in nature, it's okay with the gluons. You actually have 8 colors of gluons. They are massless, fine. Right? But this, we have the right number of gauge bosons, right? There's 4 here. There's 4 here, there. There's hope, right? But in nature, we have one massless, the photon, right? And these 3 guys, which are massive, they have between 80 and 90 GeV, amongst the heaviest particles in the model, right? There's only the Higgs and the top, which are heavier than this, right? So not even approximately they are massless. Right? They are the heaviest guys around. So we have to solve that. Right? There must be a way to implement that symmetry, because the symmetry is predicting a lot of the phenomena we see. It seems to be a good symmetry, especially the global version of it, which gives you Noether's theorem and conserved quantities. Right? But it's forbidding all masses, and we know there are masses for these particles in nature. So we need a solution, right? And the solution is spontaneous symmetry breaking. So in order to understand what this is all about, it pays to first think of systems we understand on a more intuitive level, right? So the most famous one is a spin C, right? You could build a material, right? Some magnet with a lot of spins in there. And if that is hot, right, and you're living inside that material, and the borders, right, the contours are too far away, right? You don't have any border effects. That is invariant under rotations, right? The spins are all disordered. You can rotate in any way you want. This is a good symmetry, right? But lower the temperature and what happens, right? If you lower the temperature more and more, eventually spins will start to align, right? And if you forget all complicated effects, eventually they will all align, right? And in which direction? Well, that's random, right? They will choose a direction. It's completely random which one it will be. But if you live in this very cold universe where all spins are aligned in one direction, you might conclude that there is invariance only under rotations in the orthogonal direction to the spins, but the other direction is special, right? The only way for you to realize that the 3D rotation is a good symmetry will be to heat up your universe and cool down again, because then it will align on a different direction. And you heat up again, cool down again, is a different one. And then you see the probability for alignment in any direction is the same. So the symmetry is hidden, right? It is a symmetry of the Lagrangian, but not of the vacuum. When it gets too cold, the system has to choose a direction, right? And that's what spontaneous symmetry breaking is, right? The symmetry is there, but is respected by the Lagrangian, by the Hamiltonian, but not by the ground state, right? So let's see what happens if you do that in a quantum field theory, right? This I'll do on the blackboard, because it's actually doing calculations. Let me find a... So the system I have in mind is the simplest possible, right? Just take a local U1 with one complex scalar transforming like that, right? And the accompanying gauge boson. The only tricky thing I'm doing here, now I'm worrying, right? So far I have been very sloppy with the signs. Now I'm being rigorous with the sign, and the strange thing I'm doing here is this, right? Because remember, this is minus the potential, right? So my potential is now minus mu square phi star phi minus lambda over 2 phi star phi plus phi star phi square, right? If I put a plus here, this is just potential that looks like that, right? It's actually on the real phi, imaginary phi plane, right? This is something like that, right? If both are positive. So this, right? The minimum is that phi equals 0, and it only grows from there in any direction, real or imaginary. The moment I change this sign, it gets trickier. Now at very close to the start, first the quadratic part wins, and it's going down. And then you go up. That's the so-called Mexican hat potential. And it looks like this. In fact, it looks nothing like what I will draw, because I draw very badly, but you can imagine how it would look like. Right? It goes down first, right? There's a minima, and then it goes up. you can still see the symmetry, right? The U1 symmetry is rotations on this plane. Right? This is symmetric under these rotations. But the minimum energy of the system, which is down here, is not. If I make a rotation, it moves. This point is symmetric. If I make a rotation here, this point does not move. But this one moves. So the vacuum now transforms in a different state that is also has the same energy as the vacuum, so it's a different vacuum, but is not now invariant under the symmetry. Right? And I want to describe a theory that is I want a theory that is describing excitations around the vacuum. Right? The vacuum is no particles, excitations are particles. This is not a good point to do that. Right? Because I can actually change the energy. If I say this is the vacuum, there's no particles here, I can change the energy of the system by taking energy out of the vacuum and producing something that has negative energy. That's not a particle. Right? So I want to make a change of variables and describe my system, not using this phi, which is not behaving well, but a different field that actually describes no particles in the vacuum and gives me a vacuum that I cannot remove energy from. Right? What I'm finding out is that this is not the good field to describe my system. I have to make a change of variables. Right? So let's do that. Right? What we can do first is to find where this minimum is. Right? So the first thing would be just to solve this equation with that potential. Right? That part is easy. Right? And what the conclusion is that the module of this phi, which I'll call phi 0, so keep in mind, phi 0 is not a quantum field anymore, it's just a number, right? It's just the vacuum expectation value for that field at one of these points at the bottom here, right? And this is just mu square over lambda to the power half. It's just solving this, right, for the module of phi. It's clear that it does not depend on the phase, right, only on the distance to the origin, so it's clear that it's just a number, right? And now I can define a new field, right? I can take this phi, phi of x, and define a new one, two new ones, in fact, because this is a complex field, right? It has 2 degrees of freedom, right? In this way. This is that number, right? Plus this, 1 over square root of 2, phi 1 plus I, phi 2. There is a choice implied here. Can anyone see what the choice was? Anyone wants to risk? Not actually, not the diagonal. The diagonal would look something like this, right? Here. Right? Some square here. You have to be careful to keep the, right? No, I'm going to the real direction. I'm choosing the vacuum along the real direction. You see, if I put an I here, I would be choosing it along the complex direction. One in the rotational direction and one in the radial direction. Yeah. But that's not how I wrote it here, right? In order to do what you're suggesting, it would be a different parameterization. I would call my field something like that. So this is a field that would oscillate in the radial direction, and that one, we don't need that for now. In some cases, this is a better description, right? It's easier to see stuff like that. But that's not what I'm doing. What I'm doing is I'm choosing this vacuum along the real axis here to expand around. My conclusions should be completely independent of that choice. Right? Could, in principle, make any other choice along this circle at the bottom of my Mexican hat. Right? There's a circle here Let me draw the back part of the circle, right? And any choice there should work equally. But I'm choosing this one. The way to see that is, I already told you that if I go to the vacuum, let's write it like that, right? If I calculate the value of my field in the vacuum, that will be phi 0, right, for this field. If I apply the same thing here, since I already have phi 0 on the right, that means that phi 1 in the vacuum and phi 2 in the vacuum are 0. So these fields are good, right? They are, when you go to the vacuum, the fields themselves go to 0. That means that any excitation will be a particle, and you cannot go lower than that. Right? So phi 1 and phi 2 are better fields in that way. And of course, in this point, and in this point only, phi 1 coincides with the radial direction, and phi 2 coincides with the circle, but they are actually the x and y directions. Right? In any other point, they don't coincide anymore. Right? Okay? So now, what I have to do? I have to come with these new definitions, right? So I took one field that was defined by two numbers, exchanged by two fields. So I'm doing nothing, not changing the degrees of freedom. I'm just getting this extra number. And I go and substitute this here. Just change the variables in my Lagrangian. What will happen, right? Focusing only on the potential, right? That potential will become, I'm not doing the calculations here, just write the answers, but it's just a matter of taking phi and phi star here, substituting that and expanding, right? You get something that looks like a cosmological constant here already, which is marvelous, right? It's a number in your Lagrangian. Right? You get terms which are quadratic in phi 1. But you don't get any term that is quadratic on phi 2. And then there's higher order terms that are, let's write like that, it's a cubic or more in these two guys. Right? These are the interactions between phi 1 and phi 2. I don't care too much what they are. You see, here I have both fields to the fourth, so I can have even interactions to the fourth power between those guys. Okay? But the important point here is that you get a massive phi 1, right? So the mass of this guy, if I do some cancellations here, and remember that we have defined mass in a way that the normalization for mass is usually like that, right? I'm missing that factor 2 here, so the mass for phi 1, let's call mass 1, is square root of 2 mu. But the mass for the second guy is 0. That's the important thing. So that's the Goldstone theorem, if you ever heard of it, right? That tells me when spontaneous symmetry breaking happens, you have these massless scalars. They are called Nambu-Goldstone bosons, right? So we got one here, right here. Phi 2 is, in that parametrization, the NGB, right? Nambu-Goldstone boson. If you ever see NGB around any paper on particle physics, that's what he's referring to. So these massless scalars that arise from spontaneous symmetry breaking, right? So now what happens to the gauge boson, right? Our whole point here is how do you give mass to gauge bosons, right? I can do the same trick, right? I can now substitute that parametrization in here, right? This covariant derivative gives me the interaction between the scalar and the gauge boson, right? So I'll put it there, right? I'll just take this del mu phi square, plug this definition for phi here, and figure out all the quadratic terms. The cubic and quartic terms, I'm not looking because they are interactions and can be really complicated. Right? Just waste your time writing them here. On the quadratic part, there is some simple parts. So if you do this calculation, this is actually exercise 8 already. 7 is getting this fully, right? All the exercises are listed on the notes. They will be on the website this afternoon, right? But you can do this fully, right? You get this part, you get this part. So far, so good. I'm getting kinetic terms for these two fields, right? I already know that phi 1 also gets this, so it has a mass. Okay? That's the free theory for phi 1. This is the free theory for phi 2, right? But what happens with the interaction terms? Right? You get this one. Remember, phi 0 is just a number. It's the vacuum expectation value, right? It's just a number. But you get this one, which tells me now that the gauge boson, right? What is this? This is the gauge boson mixing with a scalar. Right? But there's one more, and that's the important one, which is this one. Which is a mass for the gauge boson, right? And that does not violate the gauge symmetry, because we know that the original Lagrangian was gauge invariant, and I did nothing but rewrite it in a complicated way. Right? So these guys transform in very complicated ways, and if you do the full transformation for the Lagrangian, everything will cancel so that the full Lagrangian is invariant. But there is a mass. Another way of saying this is that the symmetry is being realized in a nonlinear way. It's not obvious, right? It's not just unitary operators canceling each other. These guys will have complicated transformations, now phi 1 and phi 2, right? If I do a U1 transformation now, phi 1 and phi 2 transform really complicated way, right? But they conceal this term, and the thing keeps invariant. But just a second, let me just finish, right? So this is the mass for the gauge boson now, right? There's also that factor 2 missing. So actually the mass is MA is square root of 2 E phi 0. And there's a very important thing going on here, right? You see that the mass of the gauge boson now depends on this vacuum expectation value, right? So how much spontaneous symmetry breaking you have, right? This is the distance from the origin here, right? If you draw an arrow here, phi 0 is the length of this arrow, right? If it goes to 0, this Mexican hat becomes just a parabola at the origin and no symmetry breaking. And it is proportional to the coupling between the gauge boson and the particle that is breaking the symmetry, the scalar. Right? This is just not any mass. I don't have a free parameter in my theory, right? Which is the mass of the gauge boson. It's not free. It's calculated from this potential, right? So mu and lambda together determine phi 0, and from the coupling with the gauge with the scalar. That's a prediction. Right? If I measure the mass of the gauge boson and I measure the scattering between the gauge boson and the fermion, these two, in principle, completely different things are related by the same constants. Right? So that's constraining. I have a Lagrangian now that has many of those blocks, right? And before I had a Lagrangian, and for each block, each of these operators has a free parameter in front, with the exception of the kinetic term. Now this Lagrangian has many, many blocks, but there's only two constants everywhere. Right? Oh, three, actually. Charge, mu, and lambda. You have way more than 3 blocks. You calculate these terms I ignore here, right? And you see there are many operators. They are all controlled by 3 variables, right? And each of these operators can, in principle, be measured independently. So this model is predictive. Right? You can tell which group made the symmetry breaking by comparing these different operators. Well, another example that I'll let you figure out. So one important thing is I can eliminate this from the theory, right? I just have to diagonalize this part of the Lagrangian, right? In this case, it's very simple because this guy transforms in a way that I can just make a choice of gauge and disappear with this term, and the mass will be just this, right? But sometimes you cannot do that. So one good exercise you can do is think of a simple theory where there's mixing like that, a theory that has like two scalar fields. But I decided to write a mass term for one of them, a mass term for the other one, and then a third term, which is, let's call this M12 square, which does this, right? A Lagrangian like that, you say, well, this guy has mass 1, 1, this guy has mass M2, but what about this? Right? In fact, there's no guy with mass M1, nor nobody has mass M2, because you have to solve this, right? So a good exercise you can do, this is, we'll call this exercise 8.5, because that's not in the notes, I just thought about it, is to, just thinking of this potential, right? Try to make a change of variables from phi 1, phi 2 to some phi A, phi B, so that you get actually this. Plus MB square phi B square over 2. Try to do this because it's an interesting way of seeing how do you get Lagrangians which have fields which are explicitly creating mass eigenstates. These fields are not explicitly creating mass eigenstates, right? But you can always do that change in variables. Right? Another example you can try to look at makes very explicit the theorems that are behind this particular example that we saw. So this is all guaranteed by theorems. Let me see if I have these in the slides. That way we save time. No. So the theorems are Goldstone theorem, and it tells me that if you break a global symmetry, say, let's call the group G, right, to a smaller, right? You use spontaneous symmetry breaking to go to a smaller global group H, right? You get a massless one massless Nambu-Goldstone boson for each generator broken. So the example we looked at, right, is very trivial because what we did here, right, was to break U1 to nothing, right? We just broke U1 in that example, right, to no symmetry, right, no group. U1 has just one generator, and we got just one massless particle. The other degree of freedom that was around is massive, as it should. Right? But you can see more complicated examples. I'll give you an exercise soon. And then a second step happens when you have local symmetries. And that is called the Higgs mechanism. That tells me now that when this breaking happens with local groups, so now I'm thinking of a local G being broken to a local H. These Nambu-Goldstone bosons will mix with the gauge bosons. So you get things, Nambu-Goldstone bosons, mixing with the gauge boson. Right? And that's what gives masses for these gauge bosons. So in our examples, it was very simple. I had only one gauge boson, only one Nambu-Goldstone boson. They combine to make a massive gauge boson. Right? So that's a simple example. Now, if you want to think of one that is still intuitive, but a little more rich, you can take a look at the example of SO3. So for SO3, you could think of a field, scalar field real now. So let's take this guy to be real, right? But it has three components, three real components, right? If I build my whole Lagrangian only out of this guy, defined in this way, phi I, right? So it's phi 1 square plus phi 2 square plus phi 3 square. This will be, if all that appears in my Lagrangian is this will be symmetric under 3D rotations in this space that I can define, this internal space, phi 1, phi 2, phi 3. Because putting only this in my Lagrangian means the whole theory only depends on the distance from the origin, right? So this is SO3 invariant, right? And you could write a Lagrangian. It's very easy. The simplest one you can think of would look like this. Phi I, again, is implicit a sum from 1 to 3 here, plus, let's write like that, minus the potential, right? And this potential could have essentially two configurations that are interesting to us, right? The first one would be something like that. So a quadratic term plus a quartic term. And in this case, right, the minimum is at the origin. There's no symmetry breaking at all. Right? But if I change this sign right here to a minus, what happens? At the start, the potential goes down as I go away from the origin, while this term is winning. Right? But eventually this one wins, and then it goes up. The minimum will be a sphere. Everyone can see that the minimum will be a sphere around the origin here. In every direction that I go, it will first go down and then go up. I cannot draw the potential because I would need a fourth axis here. I cannot draw it, right? But you can see clearly that now I can choose a vacuum at any point in this sphere. Anywhere I choose, I put a vacuum, let's say here, right? Now I have one symmetry which is left over, which is rotations around the axis that passes through this point. But if I rotate the sphere in that direction or in this direction, I have the vacuum moves. So rotations in 3D have 3 generators, right? 3 rotations. I broke 2 of them. One is left. So this theory should have 2 Nambu-Goldstone bosons for the 2 symmetries I broke, and 1 massive scalar. You can do this, and as an exercise, I put this as exercise 9. You just have to do the same I did here. Just choose one direction for the vacuum, substitute back into this potential, and you'll see that there are 2 massless scalars and 1 massive scalar here. And if I made this a gauge symmetry, 1 of the 3 gauge bosons, in fact, 2 of the 3 gauge bosons will get masses, because I have 2 Nambu-Goldstone bosons. Right? There's a whole counting of degrees of freedom that can go on here. But this is useful to understand how this choice is invariant, right? Wherever I choose this vacuum, I always break 1 rotation, break 2 rotations, and keep 1 intact. It's always easier to choose like this, right? Because in this case, it's clear that rotations around phi 1 are unbroken and the two others are broken. But if I choose it here, I broke some combination. Right? There's 3 linear combinations. I can make all of these. I broke 2 of them, and 1 is kept unbroken. So you can see that independence, the choice of where I put the vacuum, independence. I can make complicated choices that will make my algebra complicated, or simple choices, which is take one of these directions, your favorite one, and that's the one that will be unbroken. Huh? Okay, so now what is going on in the standard model? I need 10 more minutes. Fine. I'm invading people's lunch. So what is going on in the standard model? In the standard model, all we have to do is to put one scalar that is, just like the fermions, a doublet of SU2. So it transforms under SU2 as this 2-component thing. And both of these components are complex. So it has, in total, 4 degrees of freedom. And it transforms under SU2, just like the fermions, right? And under U1, just like the fermions too, with a specific hypercharge, which I choose to be 1/2, right? Now, I have to worry about the potential for this guy, which is the same as this one, the same as that one, right? With a negative, this damn negative sign right there, right? If it was positive, no symmetry breaking. The quadratic part starts negative, so you get a breaking. And in this case, if you will break SU2 times U1, it breaks every symmetry the guy transforms under, right? Since this guy transforms under SU2 and U1, we'll break both. But we'll leave one guy unbroken, just like happened here, right? One rotation was left unbroken and 2 broke. Here I had a total of 3 directions plus 1. I broke 3 of them, but not necessarily any of these individually. Actually is a non-diagonal thing that will break a mixing of SU2 with U1, right? And you left over with a U1, which is electromagnetism. The unbroken one will have a massless gauge boson. That's the photon. So the photon is not the gauge boson from U1 here. It's a combination, right? I'll show specifically which one is in the second, right? So the Higgs had 4 degrees of freedom. Because I broke 3 generators, there will be 3 Nambu-Goldstone bosons, which will give mass to the W plus, the W minus, and the Z. Right? And you're left with one massive scalar that we finally found in 2012. That's the massive scalar predicted by the theory. Is the degree of freedom that is left over is the equivalent of the phi 1 in our case here. Right? The phi 2 gets swallowed by A mu, but phi 1 is a massive particle, should be there, a massive scalar. That's the Higgs boson, right? We use little h to indicate that guy. It's one of the 4 degrees of freedom of the Higgs doublet, right? So that's what happens, right? You combine these 3 Nambu gauge bosons with these 4 guys to get 3 massive states and 1 massless one, right? In terms of the Lagrangian, we also have to choose a direction for the vacuum, right? So the vacuum expectation value in the standard model is called V. This is a number, it's 246 GeV, right? Observable quantity, right? And these are 3 fields, 3 real scalar fields, phi 1, phi 2, and phi 3. Phi 1, phi 2, and phi 3 will be swallowed by the W's, and this guy will be massive, right? So in this parametrization, the VEV of everyone is 0, and I have this number, right, which is given by the minimum of the potential. It's exactly the same expression I found there because it's the same potential, right? And then I just have to substitute these back into the Lagrangian and write the Lagrangian in terms of these new variables, right? And this is the Lagrangian I start with. So this is the part for the U1 gauge boson, the SU2 gauge bosons, the gluons. But you see, the Higgs does not interact with the gluon, so nothing will happen with the gluon. Right? It's left there because the Higgs has no color. Right? And this is the potential for the Higgs. Right? I just have to substitute that new expression there, and I'll get a very complicated thing, right? So this is the Higgs field, right? I just wrote it as a sum, right? If I take just this part of the sum and put here in the covariant derivatives for the Higgs, I'll get this expression. Remember, there are Pauli matrices here and here, right? These are Pauli matrices. So if I want to do this explicit, I'll have to explicitly write the Pauli matrices, do all the products, and I get here. And you see that I got one gauge boson that has a quadratic term, another one that has a quadratic term, and a combination of W3 and B, which is part of the SU2 and part of the U1, that is also massive. The mass is right here at the front. Right? So I got 3 massive gauge bosons. Now I just have to make a change of variables to identify these guys with the W's and the Z's, right? And find the photon. The photon is not here because I'm focusing only on the quadratic part. Again, exercise 10 is to get the other. Actually do this calculation. Just put the Pauli matrix here and get this expression. This is you have to do yourself. I could do it here. Nathan would kill me, but it's just algebra, right? And then you can do a change of variables to write the W's, the Z, and the photon. You see, there are combinations of these gauge bosons that you had, right? B is the gauge boson for the U1. W1, W2, and W3 are the gauge bosons for SU2. The photon is a combination of those 2 groups, you see? And if you substitute that back into the Lagrangian, you get these terms, right? And this is the mass for the W, the mass for the Z. You will recognize here an important thing, right? The mass for these guys depends on the vacuum expectation value, which is the equivalent of this phi 0 here, and G's. These G's are the couplings for the 2 groups. So the masses of these guys, again, are predicted by the structure that you started, right? Their masses are proportional to the VEV and the coupling of the Higgs. So if you measure how the W couples to the Higgs, and you measure the mass of the W, these 2 things need to be consistent. They are not independent. Right? And that's why we say that the standard model is very successful, because all these predictions have been verified. Right? So that's where I wanted to get today. I guess time for questions, maybe. This last part was a little quick, I admit, right? I'll put the notes in, and you have to do the algebra yourself. Otherwise, you'll never see anything, right? Have to see it and do the algebra. It's a maybe 1-hour exercise, right? There's one here. No, it doesn't. But it would take, you see, there's many transformations that you do in the middle, right? If you do, let's say, the wrong choice of the start, there will be more mixings here between those W1, 2, and 3. They will be all mixed. But then you do that exercise that I was proposing here and diagonalize on the mass. So you have to do an extra transformation to diagonalize on the mass. And then you get those, exactly those masses, right? Choosing the right direction skips that step. I already chose the direction where it comes out diagonalized from the start, right?
I have another question. I'm not sure if you mentioned at some point if this theory tell us something about the number of generations that we're going to have.
No. In the standard model, that's a completely free parameter. There's nothing in the standard model that forces you to have 3 generations at all. Right? What you have to do, because of anomalies, if anyone is curious, I can talk about that later, each generation has to have exactly those 4, 1 up quark, 1 down quark, 1 lepton, and 1 neutrino. But you could have 4, 5, 6 generations. Now we know they are not, from experiment. Because once you measure the Higgs, there's a very important fact that the Higgs in the LHC is produced by gluon fusion. Then there is this triangle of fermions and the Higgs. And all fermions contribute here, right? So if you had a 4th generation of quarks, right, you have basically 1 generation, 2, and 3. If you put a 4th one, right, you just increase the number of diagrams you can draw here by 30%. And that increases the production of the Higgs at one loop ordered by a factor 9 or 8 point something, right? And we have measured the rate of production of the Higgs with a precision better than a factor 8, right? So now we know there is no fourth generation of quarks that is chiral and interacts exactly like the other three. There are some options. You could put something that you would call a quark, but that is not chiral, for instance. You could put a heavier quark that the left hand and the right hand part interact equally, and that is not excluded. But a generation that is just a copy, it's completely excluded by now because of this measurement. Okay? Yeah. Oh, in order to do that, I would have to prove Goldstone theorem. It's not a hard proof. You find it easily, right? It's just look for proof of Goldstone theorem. You show that when you're diagonalizing masses, you take this mass, this quadratic term on the fields, right? And you go diagonalize it. You're basically diagonalizing a matrix, right? You prove that for each broken generation, there is an eigenvalue 0 in that matrix. That's the way you prove Goldstone theorem, right? So for each broken generation, there will be a massless state because there's one eigenvalue 0 in the mass matrix that you're diagonalizing, right? I think there's one there.
Just to be sure that I understood, what you do is that you have that sombrero potential.
Yeah.
And then you move yourself to the minimum. You move your center coordinate to the minimum part, and then you diagonalize. And on that diagonalization, you get the three bosons are interacting with the Higgs field, and the one that's not, and that's orthogonal.
Yeah. The combination of them that is not interacting with it remain massless. So the photon does not interact directly with the Higgs either, right? We discovered the Higgs decaying into 2 photons, but it was another triangle. So the photon does not interact directly with the Higgs. That's how we saw the Higgs first. That's the discovery channel.